Okay, so in this lecture, I'm first going to talk about a concept relating to the property of the maximum likelihood estimator. And then after that, which will serve as a concluding remark for the previous topics. And then after that, we will talk about we'll start a new topics, which is called linear model or linear regression model. Okay. So the first part is relating to the previous properties, which is called the relative efficiency. Okay, so let theta 1 hat and theta 2 hat be unbiased estimators of theta. So here, when we talk about the efficiency or efficient estimator, we need to first to check that whether they are unbiased or not. So here, let theta 1 and theta 2 be unbiased estimator of theta. And then the relative efficiency of the two parameters is defined as the variance of this estimator of, let's say we put theta 2 on the numerator, and then the variance of the first estimator. And then there are two major result. One is that if it is less than 1, that means the variance of the theta 2 hat is less than the variance of the theta 1 hat. Then we favor the estimator theta 2 hat as it has a smaller variance, so that it's more efficient than the other estimator, which is theta 1 in our case. And then if this is greater than 1, or this is essentially if you put variance of theta 1 over variance of theta 2, and then you get a less than 1, that means we favor theta 1 hat. Or let me write theta 2 hat, it's better. And then in this case, theta 1 hat, it's better. But the better is referring to the efficiency. So maybe let me bring so is it in terms of the efficient or efficiency, because it has the lower variance. Okay, so let's do an example here. So let x1 and then xn be IID from the uniform distribution with 0 and parameter theta. So here, this parameter theta is an unknown parameter, and then we are going to estimate this parameter here. Okay, so for this distribution, we have the f of x equal to 1 over theta. So if you have like a interval from a to b, then this is just 1 over b minus 1. But here we have theta and 0, so it will be theta minus 0. Okay, and then for the domain, or for the support, is that the x is ranging between 0 and theta, as this is like how it is the distribution defined, that you are uniformly the the density is uniformly over is uniform over this range here. Okay, and then we also know that the expected value for x it's b minus a over 2. So in our case, it's theta over 2. And then the variance of x, it will be b minus a taking the square and then over 12. But in our case, it will be theta square over 12. So that is the expected value and the variance for this distribution. Okay, so now let's suppose we have two parameters. One we call, so theta 1 hat is equal to 2 times x bar. So 2 times, and then the average of all these x1 to xn. So this is our first estimator to estimate this unknown parameter theta. And now let's suppose our theta 2 is defined as n plus 1 over n, and then the maximum value of x1 to xn. Okay, so here it's kind of like intuitive. So you are trying to estimate the parameter from 0 to theta, and then you can use the average about the, so if you have lots of data here and then you 2 times, and then you probably have an average somewhere here, and then 2 times the average probably will get you closer to the endpoint, as the ending point is actually the unknown parameter here. And then the other one is that you take the maximum value for your observations and then you adjust by a factor. So maybe suppose maybe you have lots of data here, and maybe the maximum value will give you a very good estimation that is getting close to the theta hat. So that is the intuition for the two parameter. So suppose you have the two parameter here. Now we want to calculate the efficiency. And to talk about the efficiency, we first need to talk about unbiasedness. Okay, so here are the two parameter, and now let's focusing on the first parameter, and then we first talk about so maybe let me put a 1 here. So the expected value for theta 1 hat is the expected value for 2 times x bar, and this is 2 times the 1 over n summation of e of x, and this is just 2 times 1 over n, and then n times the expected value, because they are identically distributed. So the expected value, it will be theta over 2 for each of them. So you have theta, and this is an unbiased estimator. Next, let's talk about the variance. So you have the variance of 2 times x bar, and then you have 4 times the variance of x bar. And then for the variance of x bar, you will have 4 times 1 over n squared, and then summation for the variance of x. And then because they are identically distributed, 4 times 1 over n squared, and then multiply by n, multiply by the variance of x. Variance of x is theta over 2, theta squared over 12. So theta squared over 12. So that the variance has the formula of theta squared over 3 multiplied by 1 copy of n. Okay, so so here we first of all know that it's unbiased, and then we also have the variance of that. Okay, so this, when we calculate the relative efficiency, this one will give you the denominator if we want to do theta 2 over theta 1. Okay. And then now let's work on the other parameter. So to work on the parameter, as you notice that we need to calculate or we need to evaluate the expected value or the variance of x. So we only know the distribution for x, but here this is a new operation which is called the maximum value. So we also need to consider what is the distribution for the maximum of x1 to xn to calculate the expected value for the maximum of a sequence of random variables. Okay, so now we need to calculate, or first we need to know what is the distribution for max from x1 to xn. So to get the distribution, we first calculate, or we first need to observe this thing to so this is essentially the definition for this is the CDF, the cumulative density function for this random variable here. So if you consider the maximum of this is one random variable, and this is the CDF for this random variable here. So you can consider this as your maybe you can consider this as y, or either way, but here I'm just focusing on the x here. So this x is just like the x when you calculate the CDF. So this part up to this x will give you the area under the curve. Okay, so that is the CDF. And then this is also equal to P of the first part of x1 less than x for this event intersect with x2 less than x, and then intersect xn less than x. Okay, so because the maximum it's less, the probability of the maximum is less than that, is also equal to the probability of each of them all less than that, because you know the maximum is less than this particular value, and all of them they are, so for the rest of the in this sequence they are not the maximum, or they are either equal, but they at least need to be less than that. So you have the probability of this event is equal to the probability of this event. And now that we can use the part or the keywords from the question or from the definition is that the x1 and x2 and all the way to xn, they are all independent. So the event of this intersect with this event and this event is essentially just the probability of x1 less than x, and then x2 less than x, and then all the way to P of xn less than x. And this is because they are independent. Okay, so now for the individual component here, these are the CDF for this uniform random variable less than that. So you can write it, and also they are identically, so let me put independent, and then they are identically distributed, so let me put identically. So you will have P of random variable x less than x, but you have n times So again, this is still the CDF for this variable less than x is equal to each of them less than x, and then they're identically distributed, so you have a power of n. Okay, and then the CDF. So here is the PDF, the probability density function for random variable x, and then for, let me put it as a side note here. So the f of x is equal to from 0 to x, and then 1 over theta dx. So this is the probability density function. You integrate all the way up to x from the lower bound. So for our support is from 0 to theta, but we are interested in the CDF up to x. So you will have x over theta, or maybe let it write it here, dt so t over theta for t equal to x and t equal to 0, you will have x over theta. So this is the CDF for this. And then now you can plug in, you will have x over theta raised to the power of n. So this is the CDF for this random variable, the max of x1 to xn less than x. So the CDF of a single random variable from the uniform distribution is x over theta, but the CDF for the max operation for this sequence, it will be x over theta raised to the power of n. Okay, so now once we have the CDF for this operation, now we can get the PDF. So the PDF of max so we can do d of f of x dx, and that will give you f of x, the lowercase f of x. So you take the derivative with respect to the random variables, and then you will get the probability density function. Okay, so the dx for this x over theta of n. Okay, and this is equal to n multiplied by x over theta raised to the power of n minus 1, and then the chain rule, you will have 1 over theta. So this is the probability density function for this max of x1 to xn. Okay. So now we have the CDF and also the PDF. Now we can talk about the expected value and the variance for our estimator. So now let's take a look at the expected value for n plus 1 over n, and then the max of x1 to xn. And this is equal to n plus 1 over n, and then the expected value for this max. So now I'm going to consider this as a random variable called x, and then multiply by this density function. So n times x over theta n minus 1 over theta dx. Okay, so this thing is the max x1 to xn, and this part here is the PDF of the max of x1 to xn. So here, this thing will essentially be the expected value for this max operation. Okay, so, and this will give us the expected value for the theta 2 hat. That's that. Okay, so for this part here is that we need to know the probability density function of that, so that we need to go through the CTF and then take the derivative to get the PDF, just so that we are able to calculate the expected value for this random variable here. Okay, so now just back to our standard procedure. We can now calculating the expected value for this term. Okay, so now we will have n plus 1. From here, the n is cancelled out. We have one copy of x, one copy of 1 over theta x, so we will have x over theta raised to the power of n, and then dx. And then for the random variable x, it's ranging from 0 to theta. Okay, also 0 to theta. Okay, so now we need to solve this integral. The idea is to set y equal to x over theta, and then dy is equal to 1 over theta dx, so that dx is equal to theta multiplied by dy. Okay, so now we have that. Let's solve the integral. N plus 1, 0. Okay, so because we are making a change of variables, y raised to the power of n, and then theta dy. So here is y, because we know y is equal to x over theta, and then x is ranging from 0, so plug in 0, you get the lower bound y equal to 0. Plug in x equal to theta, you will have y equal to 1. Okay, and then you will have the n plus 1 multiplied by theta multiplied by n plus 1 y of n plus 1. That's the antiderivative. So you take the derivative of this part, you will have the n plus 1 cancel out with that n, and then you have a power of n. And then for this thing, evaluate the y equal to 0 and then y equal to 1. So let's see. You will have the n plus 1 cancel out with that. You will have that part remaining, and this will give you, because the y can take 1, so this one will evaluate it to 1, so you will have this equal to theta, and then you have an unbiased estimator. So you will have the expected value of theta 2 hat is equal to theta. So similar to the expected value of theta 1 hat is equal to theta. So both of them are all unbiased. Now we need to calculate the variance of theta 2 hat. So for this one, let's first work on the expected value of the max for xn. Then closing that, we want the second moment because this is also needed to calculating in the variance. Okay, so for the second moment, now let's reuse, or let's call this part to as x again. So you will have, this is 0 0 to theta, and then you have x squared, and then the PDF, which is n multiply x over theta, and then n minus 1 over theta dx. Okay, so again, this is your max of x1 to xn, and then this part is the PDF of the max of x1 to xn. So you are essentially evaluating the second moment of this thing here. Okay, so now we just need to evaluate this integral. So this should be equal to, let's see, maybe now let's call the x over theta equal to, so again we need to use the change of variables. So let y equal to x over theta. So then we have the x is equal to theta multiplied by y, and then dy is equal to 1 over theta dx, so that dx is equal to theta dy. Okay, yeah, so once we have that change, and we can make the, let's bring the n to the outside, then the integral for x squared is just theta multiplied by y taking the square, and then that's that, and then 1 over theta, and then we just have y multiplied by raised to the power of n minus 1 for this part, and then 1 over theta dx is just dy, so we have that. And then let's further simplify it. We have n times theta squared from here, integrate to y of n plus 1 dy. So here y is ranging from 0 to y range to 1. Okay, then we have that. So for that integral, we have n times theta squared, n plus 2 y of n plus 2, and then evaluate the y equal to 0, y equal to 1. And then this thing, so when you evaluate 0, it cancels out, and then if 1, you will have n over n plus 2 theta squared. Yeah, so that is the variance of the, that is the second moment for this part. And now the variance of theta 2 hat is equal to the variance of n plus 1 over n, and then the max of x1 to xn. And then you will have the n plus 1 over n taking the square, and then the expected value for the max square minus the expected for the max then square. And then let me use a square bracket for that. Okay, so here the dots are the x1 to xn. So we have these two calculated. Now we just need to plug it in. So we will have n plus 1 over n square. And then for the expected value for the second moment, which is n over n plus 2 theta square minus the expected value squared. So that is the theta. The expected value for so the expected value for n plus 1 over n is equal n max is equal to theta. So we need to adjust by taking the inverse, and then you will have the you need to take the inverse, so it's n over n plus 1, and then theta. Okay. And then don't forget the square. Okay, once we have that, you just need to simplify. So n over n plus 2 minus n square over n plus 1 square, and then theta square. And then let's see. So now I'm going to multiply this inside the square bracket, and then you will have n plus 1 taking the square, and then one copy of n cancel out with that. You will have n times n plus 2, and then minus, so this one becomes a 1 multiplied by theta square. And then maybe one more, so n of n plus 2 of n plus 1 square is equal to n square plus 2n plus 1 minus n of n plus 2, and then n square plus 2n. Theta square. So when you take the difference, you will have the n square minus that plus 2n minus 2n. You only have 1 left on the numerator. You will have 1 over n times n plus 2 multiplied by theta square. So this is the variance of theta 2 hat. Okay, so we first check that they are both unbiased, and then now we can check or calculate the relative efficiency. So the relative efficiency is that you will have 1 over n times n plus 2 multiply by theta, and then divided by the variance of theta 1 hat. So the variance of this theta 1 hat is equal to theta squared over 3n. So you have 1 over 3n and then theta squared. You will have so that's the theta square, that's the theta square, and then you will have 3 over n plus 2. Okay, so the n cancel out, you have 3 over n plus 2. So this is the relative efficiency, and then you can see that this is less than 1 for n greater than 2. Okay, so in this case, we will say theta 2 hat is better. And this is in terms of the efficiency. So that means you have 2 unbiased estimator. So if you use the 2 formulation, you will get an unbiased estimator for the theta of the parameter of that you don't know for the uniform distribution. But in this case, we favor theta 2 more than theta 1 because it has smaller variance as n increase. So as you collect more data, your theta 2 is getting more, or is getting closer to the true value of theta, while the theta 1, you will have a larger variance. So sometimes you may not get a very good estimation to the true value. So in this case, by calculating the relative variance efficiency, we know that when this relative efficiency is less than 1, we know that the parameter or the estimator on the numerator is better than the estimator on the numerator, on the denominator, or in this case, theta 2 is better than theta 1 because it has a lower variance and then is reflected by this relative efficiency. Okay, so here it should conclude our work or our discussion for the maximum likelihood estimation. Okay, next let's start a new topic, which is called the linear regression model. Okay, so the idea, or for this regression model, we will have the formulation of y is equal to x multiplied by beta plus epsilon. And then here, this x, it's a n by p. So here the p is also including the intercept. So let me write down the p, or P includes the intercept. So for the x, for example, the x are, you have a column of 1. That is for the intercept. Okay, so maybe let me write down the dimension first. You will have this one p by 1, and then you will have a n by 1, because n by p multiplied by p by 1 is going to be n by 1. So that you have the n by 1 as your response, and the n by 1 for the error term. So this thing is usually called the error term. And then this is called, this is your data, or sometimes people call design matrix. This is your linear regression model's parameter. And this is your response variable, or sometimes people call this explanatory variable. But essentially, the model is in a linear formulation. So y is equal to x beta plus epsilon. So here, you can think of y1 to yn is equal to 1 for x. You have x1 to xn to x, let's say, here I'm going to use, okay, so maybe use xk. You will have that. So this is n by 1. This is n by p, and then you will have a, so maybe p beta, I'll use beta 0 for intercept, beta 1, and then beta k, then plus epsilon 1 to epsilon n, so that a column vector. Okay. Okay, that is basically the individual scalar version for this matrix vector multiplication. Okay, so now let's assume that the epsilon as a n by 1 vector is following a n-dimension multivariate normal with 0 and an identity. So that means this means the error term are all independently and also identically distributed. So each of the xi or epsilon I is following a normal with mean 0 and 1. And this is just the multivariate version, or the n-dimension version. And now, so the x is fixed, and the beta is a model parameter, and the epsilon here, we impose a normal distribution. So in this case, we just have a constant or a shift for a normal distribution. So in this case, that means the y is following a n-dimension normal distribution with x beta and then identity that. Or if you okay, so I forget. Okay, so the variance is not equal to 1, it's just equal to some variance sigma square, but they shared for all the I observations. So in this case, you will have the same variance because you just shift by a constant of x beta. This is also equivalent of saying that yi following a normal distribution with xi, which is a So here I'm going to treat xi as a like 1 by p and then p by 1. Okay. So here I'm going to treat xi as a row vector, and then you will have the sigma squared. So something like that. Okay. So we have a linear model. We let the error term be a normal distribution. So after that, we know that the y is also following a normal distribution. And then with this as the mean value and this as the covariance matrix. So this is n by 1, this is n by n, this is also n by 1, this is n by 1, so this is n by n. Okay. So now we have a linear model. Let's say we have some data that we collected, and now we want to estimate the beta. So there are two ways that you can estimate the beta. So one is through MLE, the maximum likelihood estimation. So you will have beta hat is equal to the argmax for beta. And then you have the log likelihood for the normal distribution. Okay, so that is one way that you can estimate the beta just by maximizing the joint likelihood for the normal distribution for y, because we know that the y follow normal distribution, so you can find the beta such that you maximize the log likelihood for this for this log likelihood. The other way is called the least square. So your beta hat is equal to the arg min. So the arg max will give you the beta such that this one is maximized. The arg min is also going to give you the beta such that the y minus x beta transpose y minus x beta is minimized. Okay, so this is sometimes called the error, the residual. So you want to find a set of beta after you take the model, plug in the model, and then you take the difference. So this is the true value. This will be your predicted value. And then you take the square. You want this square, the sum of square residual, to be minimized. And then this is another objective function that you can minimize to have the beta such that your error, the sum of square error, is the smallest. So this is another way you can get the estimator for the beta hat. So for the rest of the lecture, we will focusing on, maybe I will solve for the least square estimator. Okay. So let's call the L as the y transpose y minus y transpose x beta. And then you will also minus a x transpose beta multiplied by y, and then plus x beta transpose multiplied by x beta, which is the distribution. You distribute the terms to get the 4 terms in this one we call it the objective function. Okay, so this is not the log likelihood function anymore. This is the objective function, but we still denote it as L, as the loss function, or people call it the loss function. So loss function is referring to the minimized part, or the objective function just more general. You can either minimize or maximize. Okay. Okay, so now we just take the derivative for beta. So here, the first part becomes a 0 as it does not involving beta. And the second part, they are essentially the same. So we are just going to use this is just equal to 2 y transpose x beta. So So for that, you will have minus 2 times y transpose x. And then here, you will also have the 2 times. So this is like then plus a beta transpose x and then x beta. Okay. Okay, so this part is equal to that, and then this part is equal to that. So now the first term does not involving beta. Take derivative, you will get 0. The second part, you only have one beta here. They are just two identical copies, so you did 2 times that, so that you have y transpose x. And then here you will have the x transpose x multiplied by beta. Okay, so one thing to emphasize here is that you want to check the dimension. So this is 1 by n and then n by p. So here is p by n, n by p, and then p by 1. So the dimension not matching. So we need to write it a little bit differently. So 0 minus 2x transpose y I think this is a plus. 2 times x transpose x beta. So here you will have p by n, n by 1, p by n, n by p, p by 1. So that dimension is matching. Okay, so this is called sometimes it's also called the gradient. And then you want to set the gradient equal to 0. So you will have 2 times x transpose x beta equal to 2 times x transpose y. Okay. Then x transpose x multiplied by beta equal to x transpose y. So here what we want is the estimator beta hat. So when we take the inverse, we need to take from the left hand side. So you need the x transpose x inverse and then x transpose y. So here this is p by n, n by p, and then p by n, and then n by 1. So you have a p by 1 on the left hand side. So that is or people sometimes call it ordinary least square. So that is just a name for this estimator, because you are minimizing the least square objective function to get this one. So people call it ordinary least square. Okay. So just to conclude, for the discussion here, we also want to calculate the expected value for beta hat. This is just the expected value for x transpose x inverse x transpose y. So the only random variable is the y here. All the x's are considered as constant. So you will have x transpose x inverse then x transpose the expected value for y. And then the expected value for y can be calculated from the distribution. So this is equal to the x transpose x inverse x transpose, and then x multiplied by beta. So the y here, then we know that is following a normal distribution with mean of x beta. So the expected value for y is going to be x beta. And then you will have this equal to beta. So if you want, you can also call this unbiased. But the expected value for the estimator is equal to the true value beta. And now let's calculate the variance of beta hat. So this is equal to the variance of x transpose x inverse x transpose y. And then you can consider this as a multiplied by y, similar to here. So you will have the variance. So you have the A part in the front, the variance of y, and then you have the A transpose. So the A transpose is the x, because the A transpose, you need to do it from the backward. So you have x transpose transpose, just x. And then you will have the x transpose x inverse. Because this thing here is symmetric, so that when you take the transpose, it's still going to be itself. So this is just the A variance of y, and then A transpose. Okay. Now we just need to simplify it. You will have x transpose x inverse, and then x transpose multiplied by sigma, and then identity. And then you will have a copy of x, and then x transpose x inverse. And then here, this is a scalar. You put the sigma scalar in the front, and then anything multiplied by identity is just anything itself. So you will have x transpose x inverse x transpose x, and then x transpose x inverse. So these two things will cancel out, becomes an identity. So let me use another letter. So these two terms will reduce to an identity matrix, and then identity matrix multiplied by the remaining part. And then this will equal to the sigma square multiplied by x transpose x inverse. So this is P by N, N by P, and then you have a P by P matrix. So just to one last thing, beta hat estimator. As you can see that your derivation here is like the beta hat is equal to A multiplied by Y, and then the A is just x transpose x inverse x transpose. So beta hat is essentially a linear transformation of another normal random variable. So in this case, a linear transformation of a normal random variable that we have proved earlier is also going to be a normal distribution. And then the mean value is just the expected value here, expected value for beta hat, which is the beta. And then here you will have that. Okay, so here the dimension is going to be P, because this is a P by 1 and then P by P. Okay, so we know that for a linear regression model that's specified like this, when we impose a normal distribution, the error term, the y also follow a normal distribution. And then we use the least square estimator to solve for beta to obtain this closed form solution. We calculate the expected value and the variance of that, and then we know that this is a normal distribution, but with a dimension of p dimension, a normal distribution, with the mean value equal to the true value, and this is the variance for the beta hat. Okay.